So also welcome from my side to today's webinar that will show you how you can use Fluidon's virtual engineering lab to optimize your control strategies. Let me introduce the agenda for this presentation. Firstly, I will briefly introduce the Fluidon company and myself to you. Then I will show you why it makes sense and explain it a little bit, why it makes sense to use model-based development. Thirdly, Fluidon's virtual engineering lab is introduced and explained a bit before we will set up a digital twin of an excavator together and try to optimize its control strategy based on the digital twin. I will finish this presentation with a conclusion. A few words about us. Fluidon is an engineering provider on the one hand and a tool developer on the other hand. On the service side, we provide fluid power related support to our customers. To realize their ideas to solve problems. This, for example, includes system analysis, measurement, simulation, and of course, consideration of neighboring domains such as mechanics, electrics, electronics, and software. And also, we do focus on software for controlling hydraulic systems and do develop control code. On the tool side, you may already know us as the DSH Plus guys because we are vendor of this tool. DSH Plus is made for dynamic nonlinear calculation of complex hydraulics and pneumatic systems and components. And what's new is our virtual engineering lab. This is a platform for real-time simulation and visualization of digital twins, and also coupling of these digital twins to field bus networks, for example, to do software in the loop or hardware in the loop testing, or to run virtual commissioning. And from Fluidon's side, to run successful customer-driven engineering projects, we are using our own tools, of course. Fluidon is a member of the APA, and you can find further information about us on our Altair Partner Alliance page. You can see here, or directly on fluidon.com. And we do offer alliances for DSH Plus, but if you are Altair 1 member, you can automatically use DSH Plus because you are licensed. Quickly switch on my mouse pointer. Sorry for that. Okay. So one pager about me. I'm Thorsten. There's no webcam available. That's the reason why I hooked up this picture, that you have a face and have an idea who's talking to you today. I've studied mechanical engineering and worked as a PhD student and later also as postdoc at the Institute for Fluid Power and Drives of Aachen University before I learned to walk in the industry. Here I did first steps with Palfinger as a development engineer for hydraulics and got in touch with truck-mounted aerial work platforms. Then I moved on to XCMG's European Research Center, worked with different construction machines, excavators, again, platforms, truck-mounted cranes, and also mobile cranes, and was leading the competence center of cranes. Whilst with XCMG, I was trained as a CE coordinator and as a functional safety engineer. My focus of work aims on hydraulics, system control technology, and testing and application. Based on my work experience of 15 years, 11 of which I've spent in the mobile construction machinery sector, I dare to say that machine development still looks like this: a sequential processing of development tasks that are barely supported by interacting simulation tools. You only simulate when and where it is absolutely necessary, and usually you just have one specific goal for your simulation. And in this sequential structure, development results can be only brought together very lately, and you can test them only during the commissioning phase. Here, for example, the PLC, cabling, human-machine interfaces, they are tested for the first time in combination with other functionalities. But this sequential approach harbors risks. So machines are complex and several domains are involved. Electrics, hydraulics, mechanics, software, and all those involved domains influence the performance of your system. Cost for troubleshooting grows as further the development progresses. That if the machine manufacturer misses important deadlines, for example, the delivery, he's fined. So what can we do to reduce such risks? So let's bring in system simulation tools as an integrative part of the development. System simulation allows to draw a digital picture of your machine. And with a system simulation-based digital twin, you can check cross-domain interaction. You can collect real-time data, and the digital twin can run in parallel and use this data to make forecasts of the service conditions or the health status of the machine, for example. If the behavior of the real machine changes compared to the digital twin, for example, there's something happening to the valve spool is worn out, or whatever you have in mind, it is immediately detected. In addition, a digital twin opens up new possibilities for training the machine operators or training the service technicians. They can make themselves familiar with the handling of the machine by using the digital twin even before the real machine is built. However, the digital twin also forms a basis for additional functions, for new functions, or for further development of the machine, because the machine builder can safely check his ideas with the digital twin. But to take advantage of all these mentioned benefits, a central platform is needed which can execute digital twins and which is open to system simulation tools used by the machine builder. And this central platform is Fluidon's virtual engineering lab. It consists of 3 components. There's the orchestrator, then in the middle you see the real-time simulator and the hardware and the loop setup. The orchestrator organizes simulation workflows with digital twins. The powerful computer executes these digital twins in real time and calculates physical effects that are embedded in the digital twins, for example, dynamics, pulsations, vibrations, and so on. And a customer, he can connect his specific controller hardware to the hardware in the loop setup. Orchestrator, real-time simulator, and hardware in the loop setup, they can exchange data quite fast by using the EtherCAT bus, which is a real-time capable bus. And of course, you can do visualization of the digital twin real-time data in 2D or in 3D. The next slide shows some detailed information, and I would like to explain a basic function principle of the VEL. So the orchestrator docks up digital twins that have been created with any simulation tool that you have in mind, as long as such tools comply with the FMI standard. So here on the left-hand side, you can see a mechanical representation of an excavator and the hydraulic representation, and both are docked up to the orchestrator. From handling perspective, it doesn't matter whether you use individual or domain-specific models, or if you try to set up your model in a multi-domain environment. It depends on the customer's preferred choice and the simulation tool he's using. From real-time perspective, it is suggested to split up digital twins, or to split up one big digital twin into several FMIs, so that these can be executed in parallel threads. So splitting is not a big deal because you can do this either with a domain-specific or with a multi-domain system simulation tool. On the right-hand side, you can see a mobile PLC, which is connected to the hardware in the loop setup. And the software algorithms running on such a mobile PLC are responsible for controlling the excavator motion of the digital twin. The virtual engineering lab offers 3D motion of the digital twin via Unity engine or Play Canvas. And of course, 2D visualization is possible in terms of scopes or XY plots. Thanks to the open architecture to third-party products, Fluidon's virtual engineering lab offers seamless integration of simulation, visualization, and virtual commissioning. Our customers are free to choose which simulation tool suits best for their application. In any case, the virtual engineering lab is a central platform. Okay, after this, let's say, basic introduction of the virtual engineering lab, I would like to take you on a journey, and let's go on and develop a digital twin of an excavator together. And then let's optimize the control algorithm for a bucket grading functionality. I begin with modeling of the mechanic part, and I'm using MapleSim. So first I create a fixed frame as a reference point. Then I insert a rigid body frame to shift the coordinate system according to the design data, the 3D data. At the new position, I create a revolute, and I repeat this to create a total set of 3 revolute joints, 2 for the cylinder installation and 1 revolute around which the boom of the excavator can rotate. Then I install the cylinder and do some parameterization. So I can define the installation length, mass, and stroke, just for example. And for test purpose, I want to move the cylinder, and I just add a simple ramp up function to the model and also a block for a unit conversion before I simulate it. Okay, after pressing the play button, I have to wait until all equations have been solved. All of this is non-real time, of course. Then we can see a small visualization of the results. You can see how the boom cylinder extends and lifts the boom, and the boom is represented by this inclined black thin line you can see. Then I create a subsystem and define inputs and outputs. This is important for later on connection to the hydraulic model. So I use force as input. This is coming from above, and displacement and stroke as output. And for the last ones, I attach 2 probes. Okay, and finally, I can export this mechanical model as FMU, do some settings, select the inputs again, the outputs, choose some parameters, export options. So I do a co-simulation and export with solver. And now the mechanical representation of the digital twin is ready for further use. Okay, the next step is to create the hydraulic representation. This is consisting of the boom hydraulics of the excavator. For this, we need a cylinder driving the boom, and this is done via DSH Plus from our company. And thanks to the openness of the virtual engineering lab, we could also have used ArmaSim or Simulation X or any other suitable tool to create a hydraulic circuit. DSH Plus offers a lot of templates that can be modified easily. So we open a standard cylinder drive that consists of a pump and a control valve and function generator, of course, the cylinder. The function generator commands a control signal for the valve. Here you can see valve and cylinder stroke as animated movements of the hydraulic symbols, or as digital values at the nodes, or also as 2D plots on the right-hand side. Okay, now I need to modify this template for later coupling with the mechanical model. So I delete some parts. I delete the spring damper mass components and the function generator, and replace those with appropriate interfaces. So the valve, for example, will later on be controlled by a PLC and not by a function generator within this model. The cylinder needs to exchange force with the cylinder in the mechanical model, and also stroke and velocity. That's the reason why I'm creating those interfaces you are seeing here. I need to parameterize those interfaces. Label them correctly. And then I quickly Also parameterized cylinder. Here, the standard parameters, you know, displacement of rod and piston, the stroke, and so on. Then I do test-wise a simulation to see if everything is running well. And then I can, in the same manner as before, export this hydraulic model as a functional mockup unit. And by doing so, I finalize the hydraulic representation of the digital twin. Okay, up to here, we have created domain-specific models, one for the mechanics, one for the hydraulics, and now it's time to merge both together to a multi-domain, or how we call it, composite model. For later real-time calculation on the VEL, it's important that you build this composite model and that it consists of, let's say, separate FMUs, because they can be calculated in parallel threads, and this guarantees the real-time behavior. In contrast to this, if you are just creating one big multi-domain model and export this, it is most likely not real-time capable because it will be calculated as one package on one thread. Okay, to merge mechanical and hydraulic model to one composite FMU, I'm using Activate from Altair. I firstly drag a FMU block into the working area and select the previously created mechanic FMU in the file dialog. And this window also shows the available inputs and outputs that we have defined earlier. Then I drag a second FMU block into the working area and select the hydraulic FMU with all these corresponding inputs and outputs. You know, the one that we have created with DSH+. Then we need to connect both FMUs, hydraulics and mechanics, at the desired interfaces. We can mark this whole working area and combine the two FMUs to just one. Please consider that underneath this umbrella, there are still two domain-specific FMUs existing so that they can be executed in two parallel threads on the VEL. Okay, how to use the VEL, we will see in this step. So the Virtual Engineering Lab has a web interface where you can log in. Then I create a new project. And within this project, I add a real-time simulation workflow. So let's have a quick look if a real-time instance is available. Yes, we can see it here. It's a computer available. Then we need to configure the real-time job by selecting the real-time server and specifying the path of the composite FMU that we have created with Activate. We can start the FMU and see there's a message in the log window. FMU is running, yes. So now the virtual excavator is already running in the background. Later, we want to see the virtual excavator in motion. That's why we are creating a 3D visu job in addition. For this, we use the Unity engine, but we have to route the motion parameters from the composite simulation model to the Unity 3D visualization. And in this case, there are three movements, boom, arm, and bucket strokes, that are represented by three variables, output 0, output 1, and output 2. And we also have to start this visualization job. Okay, up to here, we have created a digital twin of an excavator consisting of mechanics and hydraulics, and we are running it on the virtual engineering lab. Let's now try to optimize the control algorithm for a grading operation with the bucket. What you see here are two screens. The one on the left is the PLC development environment, and the one on the right is the 3D visualization from the virtual engineering lab. This visu is fully flexible. I can rotate, I can zoom, and I can spot any position I'm interested in. From the development environment, I connect to the PLC. I log in, and I realize that there's a program already running. Virtual Engineering Lab and PLC are connected via CAN, and the digital twin provides data such as cylinder strokes and pressures. And in reality, we would get this data from real CAN bus sensors. So let's check the code. There are two big parts. One is for CAN bus communication. The other part is for controlling the movements of the machine, that is labeled automatic. And the upper part of automatic handles input information from joysticks. In our case, it's 3 sliders for boom, arm, and bucket to command the movements. And if I stop a motion too abruptly, you see it here, it causes shaking. And this exactly shows the strength of a digital twin in combination with our virtual engineering lab, because we are simulating physical behavior and we are not just moving a stupid 3D model. Okay, the code also includes access controllers, one of which brings the bucket to a desired starting position for the grading operation. This is what you see here. And the second controller controls boom, arm, and bucket movements and should perform a smooth grading operation. I have pre-selected an amplification factor for this access controller of 5. And if I start this functionality, we see it's not smooth, it's not nice, boom and arm are not correctly coordinated, and the bucket lifts from the ground far too early. So let's tune this amplification factor. Go back to the starting position. I reduce this factor from 5 to 3. And let's see what's happening. So I start the grading again. What we see is that it's, let's say, digging too deep. It's not scratching on the surface. It's just diving in too deeply. And we see that now the bucket lifts up and even opens, so it's still not the right behavior that we expect. So let's tune it further. I change this amplification factor to 1. In the meantime, I go back to the start position. And now let's check if we have finally reached our goal. This seems to be much better. With this setting, we get a well-matched behavior of boom, arm, and bucket movements. If we take a look into the bucket, we can see it's a consistent grading motion of the bucket. Okay, let me summarize the benefits of the Virtual Engineering Lab as a central platform for digital twin-based engineering. So the VL is tailor-made for the development of mechatronic systems. Engineers get a full and, in particular, domain overlapping picture of their future machine. The Virtual Engineering Lab is real-time capable and respects real physics. So dynamic effects that we have seen, shaking, vibration, can be assessed easily. Thanks to the FMU standard, the Virtual Engineering Lab is tool independent, and system simulation engineers, they can stick to the tool of their preferred choice. And validation of the control strategy, this is what we have done together in the last step. can be carried out on the real PLC in the hardware in the loop environment. And for any kind of development task for a mechatronic system in such a context, Fluidon is eager to support you. Yes, that brings me to the end of my presentation. Thanks a lot for your attention. You can see my contact details here. Send me an email, torsten.verkoyen@fluidon.com, or leave a note at LinkedIn, or visit our webpage, fluidon.com.